Hello and welcome to the final video on C5 and C7 revision for GCSE chemistry. In this video we'll be looking at endothermic and exothermic reactions, reaction profiles, bond energy calculations, chemical cells and fuel cells. To start off though, I would like you to answer these three questions. Please pause the video. You should now only be watching if you have answered all three questions. The answers are on screen now. We're going to start off by looking at endothermic and exothermic reactions. So, an endothermic reaction. An endothermic reaction is any process or reaction which causes the temperature of the surroundings to decrease. So it is any process or reaction that causes the temperature of the surroundings to decrease. By the word process, I mean something such as a change of state or dissolving. As some examples, a reaction is a chemical reaction. Now, the word endothermic, if we look at this, the word thermic refers to thermal, which is heat energy. The word endo means enter. So heat will, or thermal energy, will enter the reaction or the process from the surroundings, and that will cause the surroundings to get colder. If we have a look at an example, we're going to look at dissolving ammonium chloride in water. So I have a beaker here filled with water. Into that beaker I'm going to put a thermometer. I hope I spelled it right. I'm going to put a thermometer. So we have a thermometer in the water to measure the temperature. And at the start, we could say it is 23 degrees. I'm going to add in my ammonium chloride. I have here my ammonium chloride. And I will add it in and stir it around until it dissolves. I now have my solution. It has my ammonium chloride in it, and I can look at my thermometer again to see my final temperature. My final temperature is 18 degrees. My temperature has decreased. In this case, I have had thermal energy going into the solution, into the process, removing the thermal energy from the surroundings, so my temperature has gone down in the surroundings. We're now going to look at exothermic reactions. Now, an exothermic reaction is any process or reaction which causes the temperature of the surroundings to increase. So it is any process or reaction that causes the temperature of the surroundings to increase. Again, if we have a look at the word exothermic, we have two parts there. We have thermic, which refers to our thermal or heat energy, and exo means to exit. So thermal energy will exit the process or the reaction and go into the surroundings. We're going to have a look at an example. We're going to have a look at the example of combustion or burning. So I have here some sticks of wood, and I'm going to use a thermometer to measure the starting temperature. My temperature at the moment is 20 degrees. I will now need to use a match to light the fire. This match will provide the activation energy. The activation energy, the energy required to start a reaction. So the activation energy is the energy required to start the reaction. I can then light my fire, and I can measure the temperature at the end. My temperature at the end has gone up to 45 degrees. The temperature of my surroundings has increased. This is an exothermic reaction. There are now 4 questions on the screen for you to answer. Please pause the video to answer these questions. You should only be watching if you've answered the questions. You can now mark your answers. We're now going to have a look at reaction profiles for endothermic and exothermic reactions. And we will first look at endothermic reactions. And we're going to draw a graph. I'm drawing the y-axis and the x-axis. My x-axis is the progress of the reaction. My y-axis is the thermal energy. In an endothermic reaction, we are taking energy from the surroundings and it is entering the reaction. And that means our reactants will have less energy than the products. We always start by first drawing a line for our reactants, which we have along here. This shows the amount of energy they have before the reaction. Because it is endothermic, we end up having more energy in our products. So our line for products will be higher up. We now need to connect these lines. Now we cannot just draw a straight line between them. We first need to go up, and we have a hump going over the line there and then going back down to the products. And we can use this graph to tell us various things. From the energy of the reactants to the top of the hump is our activation energy. It's how much energy we need to start the reaction. Our overall energy change, we can look at from where the reactants are up to the products. So this is our overall energy change. We have some rules for our endothermic reactions. First is that the products store more energy than the reactants. So the products store more energy than the reactants. Second, we have a large activation energy. We have a large activation energy. The energy required is more than the products have themselves. It requires a large activation energy. And finally, we have an overall positive energy change. We have an overall positive energy change. We'll now look at an exothermic reaction. And we're going to do the same thing. We're going to have our y-axis and our x-axis. Again, we're labelling them the same. We've got our progress of reaction and we've got our thermal energy. And this reaction, energy will exit from the reaction or process. And our reactants have more energy, so their line will start higher up. The products will have less energy. So we have our reactants and we have our products. Now, just like in an endothermic reaction, we need to have an activation energy. We need to increase the amount of energy. So we will first go up with a hump before coming down to the products. Now, this line from the reactant up to the top of the hump is our activation energy. And from our reactants down to our products, this is our overall energy change. And that thermal energy will have gone into the surroundings. Again, we have some rules for exothermic reactions. In this case, the reactants store more energy than the product. The reactants store more energy than the products. It has a smaller activation energy. We have a smaller activation energy. And we have an overall negative energy change. We have an overall negative energy change. There are now 4 questions for you to answer. Please pause the video to answer these questions. You should now only be watching if you have answered all 4 questions. The answers are on screen now. We're now going to have a look at some bond energy calculations. Now, bond energy calculations allow us to determine whether a reaction is endothermic or exothermic. And this relies on knowing the energy required to break a chemical bond. We measure the energy required to break a bond in kilojoules per mole. So the energy required to break a bond is measured in kilojoules per mole. In your exams, you will be given the energy required to break the bonds or the overall energy change to find out a missing bond. We're going to have a look at an example. So we're going to have a look at hydrogen plus iodine to make hydrogen iodide. This is now balanced. We're now going to work out if this is endothermic or exothermic. You are given the bond values. So an HH bond is 436 kilojoules per mole. An II bond is 151 kilojoules per mole. And a hydrogen iodide bond is 295 kilojoules per mole. Now, when we are working out these equations, we need to determine what bonds are broken and which bonds are made. It's always best to draw it out. So we've got hydrogen, we've got iodine, and we've got hydrogen iodide. Remember, we have 2 of them. We can then work out which bonds we need to break and which bonds we need to make. We need to break bonds between the hydrogen atoms and the iodine atoms, and we need to make the bonds between the hydrogen iodides. Let's make 2 of them. And we can work out the energy we need to put in, which is on our left-hand side, and the energy that we will get out from making those bonds. So if we have a look at this now, we've got 436 kilojoules per mole plus 151 kilojoules per mole. That is our energy in, which gives us 587 kilojoules per mole of energy going in. Our energy going out is where we are making these bonds. So if we're making a bond, we are giving energy out. And we have 295 kilojoules per mole for each one of these. So we have two of them. Because we're making two of these bonds, we have two of them, which gives us a total of 590 kilojoules per mole. To work out the energy change, we need to do our energy in minus our energy out. So our energy change equals our energy in minus our energy out. So our energy change will equal 587 kilojoules per mole minus 590 kilojoules per mole. That will give us an energy change of minus 3 kilojoules per mole. Because this is a negative energy change, an overall negative energy change, this is going to be an exothermic reaction. A negative energy change is an exothermic reaction. Now please pause the video to answer these questions. You should now only be watching if you have answered all of the questions. The answers are now on screen. We can use the reactivity of metals to make chemical cells, and we can combine those cells together to make batteries. Now, if we take a beaker and fill it with a salt solution or dilute acid, so a salt solution or dilute acid, and place two electrodes in there. Now it is important that the two electrodes are made from different metals. We will use zinc and we will use copper. We will then connect these electrodes with a wire with a bulb attached to them as well. Now because zinc is more reactive than copper, it is more likely to lose electrons. So a more reactive metal is more likely to lose electrons than a less reactive metal. Because it has lost electrons, we can say it has been oxidized. The electrons will flow from the zinc to the copper. As a result, our more reactive metal is our negative terminal. The electrons will flow through the wire and transfer the energy into the bulb, causing it to light up. And this will continue until either the copper or the zinc has run out. The electrolyte solution allows the electrons to transfer from the copper, keeping us with Cu2+ ions to attract those electrons. We have two types of batteries or cells. We have rechargeable cells and we have non-rechargeable cells, such as the alkaline cells. A rechargeable cell can be recharged. It can be recharged because we connect it to a power supply, and that causes the electrons, or we can force the electrons to go back the other way to our more reactive metal. Alkaline cell cannot be recharged because the reaction is irreversible. Please pause the video now to answer these 5 questions. You should now have answered the questions. The answers are on the screen. We're now going to have a look at hydrogen fuel cells, which are a great way of generating electricity with minimal greenhouse gases. We only produce water vapour, which is not a major greenhouse gas. Now we have the setup here. We have 2 electrodes, which are here and here. They're both made of graphite. We have an electrolyte, which is normally potassium hydroxide. And that contains hydroxide ions that are free to move around. On our left hand side, we have hydrogen gas coming in. We have hydrogen gas coming in, and the hydrogen will diffuse through the graphite electrode. As it diffuses through, it will lose electrons to become an ion. Those electrons will be taken up and will flow around the circuit. We now have H+ ions that have formed in the electrolyte. They will combine with the OH- ions to form H2O. The H2O, or water, will then move out past the negative electrode back into here, where it can be removed from the system, and we get water given out. We have a half equation we can write here for the negative electrode. So we have hydrogen will react with hydroxide ions to form water, and we obviously lose electrons as well. Now, at the moment, our equation is not balanced, so we need to balance our equation, and we have 2H2O, also 2H2 plus 4OH- will make 4H2O plus 4 electrons. And this is what happens at the negative electrode. We have the formation of water, and we gain 4 electrons that can flow around the circuit. Those electrons will pass through and will move through. The symbol up here, the M, is for a motor. We can use it to drive a car. We come down here and we have our electrons continuing to flow down. On this side, we have oxygen gas coming in. So we have O2 gas coming in. The oxygen will diffuse through the electrode and combine with the H+ ions to form OH-. So it will gain electrons at this stage from the positive electrode to form negative ions, and we can then combine with the hydrogen ions to form OH-. So at our positive electrode, we can have another equation going on. So we have oxygen will combine with water molecules that are in here to form, sorry, we've missed out a step there, as well as gaining the electrons to form OH minus ions. We have water will react with oxygen plus gaining the electrons to form OH minus ions. We still need to balance this equation. We have our water, we have 2 water molecules, we'll have 4 electrons and we will form 4 OH minus ions. And that replaces the 4 OH minus ions that we used at the negative electrode to make the water. You can see that this reaction can continue. The only product we have is water as water vapor, which is not bad for the environment at all. Please pause the video and answer these 5 questions. You should now only be watching if you've answered all 5 questions. The answers are on screen now. Thank you very much for watching. I hope it's been useful. Take care. Bye bye.